Hello, and let us talk about units. This is the first concept we have to master, we have to understand very well. How to go from one system of units to the other. I'm talking about how to go from imperial system of units, such as feet, such as inches, feet, miles, to meters, millimeters, or from pound mass to kilograms, or pound force to newtons. So let's go ahead and see how we do that. So there are definitions. There are things that we have to either remember or look up that are already established. So 1 feet is zero point 0.3 meters. Okay, precisely 0.3048 meters. This is like that, and when we have to convert from feet to meters, we do use this parameter, or if we convert from meters to feet, we go the other way around. Okay, so remember that also 1 meter is 100 centimeters. 1 meter is 100 centimeters, and 1 meter is 1,000 millimeters. Okay, the same way that 1 feet is 12 inches. Okay, so that is just so that we can remember that from one system of units, imperial, to international system of units, feet and meters have that correlation. 1 feet is zero point 0.3 meters. 1 mile is 5,280 feet. Also, 1 mile is 1.6 kilometers, which we know that 1,000 meters is 1 kilometer, and that is because the kilo prefix means 1,000. All right, mega. So let's do something here. Kilo equals 1,000 kilonewtons, 1,000 newtons. Kilograms, 1,000 grams. Mega is 1,000,000. Meganewtons is 1,000,000 newtons. And you can have things forward. So you can have 10 to the 9, 10 to the 12th, penta, and things like that. You can also have smaller, usually in other fields like electronics. You can have micro. So micrometer is 10 to the negative 3 meters. All right. Actually, that's millimeters. Millimeters is 10 to the negative 3 meters. And 10 to the negative 6 meters is micrometers. Okay, so forget this. 10 to the negative 3 millimeters. 10 to the negative 3 is milli. So millimeters, milligrams, millinewtons. This could be different things. Millinewtons, milligrams. Micro, which is mu, a Greek symbol, is negative 10 to the negative 6. Milli, micronewtons. Micrograms, this is like in biology, forces in our brain. Microvolts, the signals in our brain. We can have smaller too. We can have nano, which is 10 to the negative 9 nanometers, 10 to the negative 9 meters. So this is all the scales that we can have. Nano, micro, micro, milli, micro is the same as micro. Nano, micro, milli, kilo. We can have even centi. Centi is 10 to the negative 10 is 100, 10 to the power of 2. Centimeters, centipoise, some viscosity measurement. Mega newtons is 10 to the 9. and then 10 to the 9, no, 10 to the 6, I mean, mega is 10 to the 6, in 1 million. 10 to the 9 is gigabytes, giganewtons, etc. And obviously 1,000 mega is 10 to the 9. So 1,000 mega is 1 giga. So there are different ways we represent the same thing. Okay, so since 1 feet is 12 inches, we can move from inches to millimeters very easily because 1 inch is 25.4 millimeters. All these things are units of distance. So 1 inch is 25.4 millimeters, 1 mile is 1.6 kilograms, and 1 mile is 5,280 feet. So if you multiply, so 5,000, I don't know why I say 500, 5,280 feet to kilograms, we know 2 kilograms, 2 meters, 2 kilometers, I'm sorry. So this is feet, and we know that 1 feet or 1 foot is 0.3048 meters. So 5,280 times 0.3048 will give you 1,609 kilometers. So don't get confused. In international system of units, if you take away the kilo, it will be 1,609 meters, or the kilo will be, that's why we have the dot here. A kilo at multiply 1,000 is 1.6 kilometers. So 1 mile is 1.609 kilometers. Okay, so that's the units of distance. You just want ways to combine or to switch from one system of units to the next, and they're already defined. 1 inch is always going to be 25.4 millimeters. 1 feet will always be 1 foot will always be 12 inches. But there are other less common units, such as 1 slug. 1 slug is 14.59, or we can also approximate this 14.6 kilograms. So that's why we have the word sluggish. So kind of heavy, slow moving, things like that. And actually, the full units of slugs, or of 1 slug, is 1 pound per second squared divided by 1 foot. So 1 slug is 1 pound mass second squared divided by foot. So actually, I find it easier to remember that it's 14.6 kilograms. 1 pound mass is 0.4536 kilograms. Okay, so if you're 150 pounds, if you jump on top of the scale and you find out that you're 150 pounds mass, then if you multiply 1 pound mass times 0.4536 kilograms, this multiplication will give you your weight in kilograms, which I don't know, it will be around 67. We'll have to use the calculator for that, approximately, whatever this is. Between 65 and 70, I'm guessing. It's not quite the half. So whatever your weight is in kilograms, it's just the pounds times 0.45. That's the factor. Now, 1 pound force, in a lot of times, for convenience, 1 pound mass is going to be LB from libre or libra. LB is the short for pound, from French libre. And pound force, they add an F. A lot of times they add the F at the end. So people know if it's pound force or pound mass. If they give you, of course, in international system of units, it's simpler because Newton is force, kilograms is mass. But in the imperial system of units, pound is the basis for both, but it's pound mass and pound force. So we're lazy and we don't say I'm 150 pound mass. No, I'm 150 pounds, just 150 pounds. But when you see a turbine, when you go and jump on an airplane and you see the thrust of a turbine, they will tell you is, I don't know, 50,000 pounds. That is pounds force. And 1 pound force is 4.448 newtons. Okay? All right. Let's go to another concept, which is moment. And just FYI, in case you haven't heard moment or momentum, moment is different than momentum. With an U. Moment is force times distance. Force times distance is moment. Momentum, which usually is small m, not mass, is mass times velocity. Okay, so that's why you hear sometimes like people talk and say, "Oh, we have to hurry up. We don't want to lose momentum." This is a concept used in in dynamics, and this is a concept used in statics when things are not moving. It's a force and a distance. Okay, momentum is the mass going at certain velocity, so they are different. But since right here we're going to talk about moments, we can transfer pound force. So it's basically a units of force and the units of distance. The units could be miles, feet, inches, whatever. And the unit of force could be either pound force or Newton. So 47 pound inches is, and we want to transfer that to newtons. So very easy. The value, the magnitude is going to be the same, obviously, but we just transfer that to Newton meters. So 1 pound is 4.448 newtons, and 1 inch is 25.4 millimeters. If you multiply these three things, you're gonna get 5,310 Newton millimeter. Or you see that you can do a kilo here because you have 1,000. So 5.3 kilo, sorry, this is a 3, kilo newtons per millimeter. But that doesn't look, that is not a conventional unit. So either way, the other thing that you can do is just 5.3 newtons and the 1,000 as applied to the millimeters. 1,000 millimeters is 1 meter. So 5.3 newtons per meter, which is what we have here. So this is just a conventional way of transferring from one system to the other. Very easy. The other way around, if you want to transfer 40 newtons per meter to pound feet or pound inches or whatever you want to do, is just following the parameters that we already know. 40 is the magnitude, we don't change that. And we know that what Newton, 1 Newton is 1 pound force. And we know that 0.3048 or 0.3048 meters is 1 foot. So if you do this, it will give you, use your calculator, and that will give you the amount of moment in pound feet. Pound feet. Okay, so if you combined the units that we have, we will have physical quantities. So remember, the main units that we can have are length, distance, which is inches or meters. We just talked about that. Time, which is always in seconds, or of course could be milliseconds, but it's seconds is the root unit. The other one is mass, which is in either pounds or grams. It could be other stuff, but this is the basic stuff, the pounds and grams. If you combine them and you start squaring them and multiplying them by themselves and dividing them, you're gonna have different things. So for instance, acceleration is length divided by time squared. So you can have feet over second squared, or you can have meters over second squared. Okay, and basically 1 foot over second squared is 0.3048 meters over second squared. It's nothing new. We already know that 1 foot is 0.3048 meters squared. Inches per second squared. Then we already know that 1 inch is 25.4 meters. So the units have to be consistent. Has to be length over time squared. Area, so let's do here, length over time squared. Area is length squared, right? If you have a rectangular, is this distance times that distance. This area, the area is length squared. So it's feet squared, inches squared, meters squared, etc. So here the only thing you have to do is 0.3048 squared is 0.0928. Remember, if a number is less than 1 and you square it, it's actually going to be less than 1, much smaller than 1, not bigger. It's only bigger if it's greater than 1. Inches squared are this 25.4 squared, 64 or 645.2 millimeters squared. Energy, and has the same units of work, which is not the same concept, but they're the same units, are pounds times feet, or feet pounds force, and this is joules, okay? And this is joules is kilograms meter squared second squared. So basically work is mass times length squared time squared. Or energy, the amount of energy that you eat, what you drink, which joules is also a unit of calories. So 1 calorie is close to 5 joules. The calories that you see when you eat something, that is energy. And calorie could be transferred to joules, and joules is basically a unit of mass. Of course, when you eat something, that something has a mass. If it's a potato chip, a burger, that has a mass that you're eating. The length squared, so is calculated not in volume, not the volume of the object, but the area, so is by area. So because the simplest thing you can have is, say, a potato chip. So assume is zero thickness, it's just a surface, which they have a little thickness though, but assume is zero thickness. You can account for it because it's length squared. And time squared, because is coming from a force. And forces have time squared component. So it's pretty interesting if you look at the physics. If you go back to your x, y, and z, and there's an alternative plane going in some other direction, which is time, you have 4 dimensions. If you start combining them, you're gonna have different quantities. So if you do x one direction and other direction, that's gonna be, so for instance, if you have a rectangular shape living here, you're gonna have direction x, direction y, that is 2 directions. So of course that's gonna be length squared. But time, you can square the time even though you only have one time direction. So it's pretty interesting. nonetheless, you can have them multiplied and divide themselves, kind of like in acceleration. You have length divided by time squared. Velocity, velocity would be length over time. Okay. Force, we already talked about this, is newtons, which is mass times length divided by time squared. Kilograms, meters, second squared. Or is not very, I don't I don't see these very often, but you can have kilopounds, and of course pound force, which we do see that all the time. And notice that I keep putting the F for force to remind you that this is this is a pound force, but you will not see the F a lot of. It's not conventional to see the F. You have to know that if they're talking about a force, is pound force, which is not the same as pound mass. Impulse is feet times seconds. Okay. This is we have to check if impulse is force. I think this is a typo. Let me double check here because impulse should be let's impulse units of impulse. Let me double check this guy because this one is saying that is feet times seconds, and this one is saying that is force times seconds. So is this times second times distance times time, or is force times time? So we'll have to check this. We'll have to Google it in a minute. There's a typo here. Length, we already know is distance, feet, miles, meters. Mass, you can have ounces of mass, but you can also have ounces of liquid. So an ounce can go from volume, so length, cubic length, or it could go to mass, which is just its own unit, mass. And mass, so ounces of mass are 28.35 grams, or our point, or a pound mass is 0.4536 kilograms, where you saw this. Slug is 14.59 kilograms. 1 ton is 907.2 kilograms. Okay, there's another one that they're missing here, and it's vibration. So vibration, like a bridge, like an engine, has units of length divided by time. It's the same units of velocity. So it's inches per second or millimeters usually per second, because it has to usually pretty small. So it's length over seconds, over time, I mean. Moment of force. This one is the one that we just talked about. It's abbreviate is just short for moment of force. We just call it moment. But the real term is moment of a force. So it's a pound times a foot is force times a distance, and 1 pound foot is 1.356 newtons per meter, or 1 pound inch is 1.1130 newtons per meter. Why is not the same? Because this is not a one-to-one correlation. There's 12 inches in 1 foot. It's not 10 inches in a foot, it's 12. Therefore, these numbers are different, so don't get confused. Moment of inertia. This is a pretty interesting concept because we have length to the fourth dimension. So even though we only have 3 physical dimensions, we have we have 4 dimensions of moment of inertia. And what that means is that if we have an area, say a rectangular shape or any shape, that has L squared, doing some work or some displacement, doing something, that area, the moment of inertia is whatever happens between those two instances multiplied. So L squared times L squared is going to be L fourth, right? You keep the same base and you add the exponents. So moment of inertia is, if it's an area, is to the fourth. If it's moment of a mass, it's also pretty interesting because it's the mass times the area. So mass times length squared, or in this case is pounds. So mass times distance times time squared. Which, let's go ahead and do something here. Let me check. Impulse units. Newtons per second. Okay, so that is correct. And imperial impulse. Okay, so is length times mass divided by time. Yeah. So it's length mass divided by time. So length is meters, mass is kilograms, and time is seconds. So kilograms times meter over second. Okay, that makes sense. Let's see somebody else telling me what that is. Impulse. Yeah, newtons per second. That is correct. Okay, so I feel that we have checked that impulse is newtons per second. It's just mass times, so it's the velocity at which a mass is traveling, that is impulse. All right, the other concept that we wanted to check was so this is actually pound force times second. Okay, the other thing we wanted to check was moment of a mass. Kilograms meters per second. Kilograms moment of a mass units. Moment. Oh wait, no, that we know. Sorry, we already know that is correct. What we know is the moment is force times distance, but we need the moment of inertia from us. Moment of inertia. Mass. All right. It's saying inertia, rotational inertia. The rigid body determines the torque needed to desire angular velocity. Moment of inertia. So it's kilograms meter squared. Let's see. Kilograms meter squared. Yeah. So why is this one having seconds? I don't think that's true. Well, it does. Other units is SI. We have, oh, I see why. Okay, because this is pound force. Okay, got it. Okay, so I got confused. I apologize. Yes, so that makes sense. So even I was getting confused. Pound force. Yeah, because pound force already has time that is going to be canceled here. So it will be, at the end, it will be a mass and length squared. Okay, so in doubt, please check. Momentum, we talked about that is going to be a pound weight. times, no, actually, this is pound force 2 times velocity times time. Sorry, another unit since imperial units is a force times v time versus in international system of units. And now you start to see why people like to use international system of units in physics. It's a little more straightforward, I believe. You have a mass times velocity, which is a length over time. Okay, so this is momentum. Power is watts, which in international system of units is very simple. Is joules over second, the amount of energy or amount of work that you can do in time, versus in international system of units, it's going to be feet times pound force over second. And I know it's pound force because in joules there's newtons. So you can tell that I don't use these imperial units very often. I always use international system of units. And I believe I'm just homeworks and exams and quizzes will just mostly be try to do it with international system of units we could because it's way easier, more intuitive. So stress, which we'll see, stress and strain, we'll talk about them later because this has to do with the formation in a body, in a system, has the same units of pressure. And pressure has units of pascals, which is the same as a force applied on an area. And a force is newtons, and an area is length squared. You can also have pound, so this is called PSI, pressure, so it's pounds per square inch. Velocity, we talked about this already, is length over time, miles per hour, meters per second. Volume is length, it's cubic length, so meter cubic or cubic meter, inch, cubic inches. And for gallons, there's liters and gallons. Okay, now this is the other concept that after units, we're gonna move to coordinate system now. And if you have a system that you want to analyze, you have first of all to choose where to put the system of coordinates. If you put your system of coordinates here, which is okay, x, y, and z, you have to know that whatever happens, the forces that are applied on this side from this origin to the left are going to be negative nx. All the resultant forces, all the computed forces are going to be negative ny because this is the zero. It's positive vertically to the top, is negative vertically to the bottom. And z is going to be also negative because the system is behind the origin, so it's negative z. So perhaps more conventional, more intuitive, a better place to put the coordinate system would be a place where everything is positive. So here you have all your x's are positive, or your y forces will be positive, and all your z forces will be positive. So at this point right here. So if a force negative F1 is applied, all the distance on the y coordinate system is positive. And if a force was applied here, parallel to z, it will be computing positive forces. So you can also put it here if you feel like it's more intuitive, the center of the geometry, and just have x and y and z. So you have positive and negative in x and y, positive and negatives in z, but all your y's will be positive. So you can or you can choose it wherever you want. Just make sure that you don't get confused. Okay. Now there's another concept that we have to also go over in it, that is numerical accuracy. So if you notice, I keep rounding up to the first digit, but sometimes that is not wanted. So for instance, 1,000 pounds divided by 75, sorry, 100 pounds divided by 75,000 pounds is 0.0013. So that actually is 0.013%, which is somewhat significant depending on what you're doing. If you want to know what is the deformation of a helicopter when it falls, that number is very important to know. And it hopefully is the smallest possible number that you can design for. So that brings me to the point of numerical accuracy is very important where you're gonna do sensors. So if you're gonna do civil engineering, mechanical engineering, you have to test the deformation of airplanes or bridges. Then you're gonna put a sensor to measure the deformation, and then they have to be pretty accurate. So just to see if we can play this video, this is, I'll share the slides so you can see them. Oh, what's going on here? Okay, let's go ahead and see it again. So this is a controlled drop of a helicopter chassis. And they want to check what's the deformation of the structure, what is the force that the bodies, that the systems and the dummy bodies will be receiving. The helmets, the chairs, the consoles, everything. So in that case, for instance, let's do, for example, you have, let's say the helicopter, this is the ground, and the helicopter just um, landed. Notice that it didn't have any wheels or anything, it was just a crash test, which is pretty common in aviation. Okay, so somebody will give you the forces, and they're in the book, they will tell you that there's a force right here. And remember, the force is mass times acceleration. Mass is the mass of the helicopter. Acceleration is the velocity, the acceleration at which it was dropping. That could be computed by the systems in the helicopter, velocities and times and etc. And all even sensors that just give you acceleration, accelerometers. And there's a force here. There's a friction here. We'll talk more about these things. There's a friction here. This force to stop it. You can put wind, you can put other stuff. But anyway, the point here is that this very simple system will help you determine what is the force, how, if it's dynamic systems, how much was the travel. If it was just the impact, you just care about this force and that force. You want to, depending on how, if you want to compute the stress or the strain, we'll talk about those later in this class. You want to know what the material properties of the helicopter are. It's probably aluminum. So you're going to have elasticity modulus, you have some shear modulus, um, you're going to have some ratios of deformation, etc. So these things are extremely valid, extremely useful to decide how to design the helicopter for better um, resilience or for more secure scenarios, because that data will be used for designing another iteration of the helicopter. And the accuracy is if your sensors are giving you errors between 0 and 10%, you know, if you NASA calls you to help you with the test and you say, well, my value could be between 1 Newton and 10 newtons, you're gonna be like, whoa, no, that's not gonna be good enough. In their case, they're probably between 0.001 Newton and 0.1 So plus minus 0.001 Newton, meaning that if the sensor gives you 150 newtons, then you better, if you do it again and you test again, the value will not be 160, 140, will be maybe, if not everything was the same, will be 151, 148, but it will be very close to 150 because your sensor has an accuracy of 0.001 Newton. And the drift or the offset is just because of things that changed during the experiment that you couldn't control, like wind speed or air humidity, or if it was started to rain, whatever. But the sensor itself has to be very accurate. So you have to choose when to use high accuracy. For this class, we're not necessarily going to use extremely high accuracy because if the answer is 147.3, then we just can say 147 newtons. That's okay. But in other areas, make sure that you have accuracy accounted.